So I'll start now. So today what we're going to do is a little bit of a different topic from what we discussed the last few times. So today what we're going to do is look at one of the couplings between SLE and the Gaussian free field. And so here's the idea. So you should imagine that we have a domain which is in the complex plane. And let's suppose that we have a function h, which is defined on our domain. So this is not the Gaussian free field, but rather this is just, this is a continuous real-valued function. Okay. Then if you have a function like this, you can always associate with it, with your function, a vector field. And the way that you get your vector field is that you consider just the complex exponential e to the I h of your function. So explicitly, this is just the vector field where in the x direction, the vector is pointing, well, the magnitude of the vector is just the cosine of the function at z, and in the y direction, the magnitude is the sine of your function. Okay, so if your domain, for example, is a square, like this, so I've just drawn a square here, then at each point you have a unit magnitude vector, which maybe looks something like this. Okay, and you get some kind of vector field. Okay. And then I'm going to say that the flow line of h starting at z, this is just what you get when you flow along this vector field. So it's just the solution to the ODE, say d dt eta of t is equal to e to the I h eta of t, where the path initially is at z. Okay. And what we want to do now, so our goal for today, is we want to make sense of the flow lines when h is not a continuous function, but rather h is an instance of the Gaussian free field. Okay, so that's what we want to do. And of course, the kind of difficult thing in all of this is that when h is a Gaussian free field and not a function, so kind of the big challenge here is that this h is a distribution and not a function. So it doesn't really make sense to write down e to the I h of z. So this is not, it's not a priori defined what this even means. Now, if you were trying to do this, trying to make sense of these flow lines, kind of the natural thing to do would be to do, what Remy was talking about when you try to construct the Liouville quantum gravity measures. And that's that. This is sort of the natural first approach to this. You could try to consider the vector fields that you get when you take your Gaussian free field and for a fixed value of epsilon, you just average it on circles of radius epsilon. Then, as we saw yesterday, this function that you get when you consider these circle averages, this is a continuous function of z. So, so its flow lines, they exist. There's no trouble making sense of these. And then what you'd like to do is you'd like to try to show that these paths actually converge when you take a limit as epsilon goes to 0. And if you could show that, then this would be kind of the natural definition of what a Gaussian free field flow line should be. But might seem sort of surprising if you've seen this the first time, but this is actually an open question. Nobody knows how to get this approach to work. So an open problem is to is just to make this approach rigorous. This seems to actually be quite hard, quite a hard thing to do. Okay. So what we're going to do, rather than take this approach, is we're going to take sort of an indirect approach to constructing these Gaussian free field flow lines. And here's the idea. So what we're going to do is we are going to first think a little bit about, let's go back to the case that h is just a continuous function. And we're going to try to use this sort of standard case to guide us in how we might try to construct the Gaussian free field flow lines in an indirect way. And the point is that in this case, these flow lines have two important properties. That are going to let us figure out how to do the Gaussian free field construction. The first property, the first sort of observation, is that the values of your function h, these are determined along a flow line eta by the path eta itself. Okay, and the reason for this is that if you see the flow line associated with a continuous function, then you know the direction in which all of the arrows are going along the path, and that's enough information to recover the values of the function along the path. Okay, so this is one important observation. And the second important observation is that if you change your function h off the realization of a flow line eta, this does not change eta. Okay, so going back to this picture over here, if I draw in one of these flow lines, maybe in red, so let's say I draw in this flow line here, then if I change the direction of the arrow is kind of in this region, away from the red path, then this is of course not going to change the red path. Okay, so the flow lines only depend on the function values along their trajectory. Okay, and so now using these two properties, what we're going to do is we're going to try to reverse engineer a construction of Gaussian free field flow lines. So when H is actually a Gaussian free field. Okay, so to construct these flow lines, what we're going to do is we're going to start off with a couple of guesses. So the first thing that we're going to guess is that, number one, they should be SLE-type curves. And the reason for this is that, as we did 2 times ago, we saw that the Gaussian free field, this is conformally invariant. And it also satisfies a Markov property and we saw in Vincent's course, so we saw in the SLE course that properties of this type characterize SLE. These properties actually single out the SLE curves. Okay, so that's the first guess, is that these should be SLE. And the second sort of guess is that if we look at the conditional law of the Gaussian free field, given one of its flow lines, then what it should be given one of the flow lines, so what it should be is that of a Gaussian free field in the remaining domain with boundary values what they would be if if this path was a flow line of an ordinary continuous function. Okay, and the reason for this is what I just I said before, and that's that in the case of an ordinary continuous function, changing the values of your function off the range of the path don't change the flow line itself. So in other words, if you see the flow line, it doesn't tell you anything about what the function is doing off the range of it. And put in the Gaussian free field language, this tells you that all that you should get from seeing the flow line are what the boundary values of the Gaussian free field should be along the path itself. Okay, And so using this idea, what we're going to do now is describe a sort of two-step procedure for sampling the Gaussian free field along with one of these flow lines. Okay. So this leads to the following procedure for trying to construct a Gaussian free field. So what do you do? So the first step is we're going to sample an SLE curve. Let's say eta, and it's going to go from 0 to infinity in the upper half plane. So let me draw a picture over here. So we have the upper half plane. This is the origin. And the first thing I'm going to do is draw this SLE curve, like that. OK. Now, once that's fixed, what do I do? I'm going to pick a Gaussian free field in the complement of eta. So this is eta right here. And once this is fixed, I'm now going to sample a Gaussian free field in the complementary domain. And its boundary conditions along eta given by what they would be if eta was a flow line of a continuous function. Okay, so if this was actually a flow line of a vector field of the form e to the IH where h was a continuous function.
Jason?
Yep.
Does this work if kappa is bigger than 4?
Yeah, if kappa is bigger than 4, the general mathematical construction is the same. The only difference is that the interpretation of what this sort of means is different.
Would you be sampling the GFF outside of the hull then? Or would you also be sampling it inside the little bubble?
You would also be sampling it inside of the little bubbles, right? Okay, so in this first step, what have we done here? So at this point, what we've done is we have described a distribution valued random variable let me call it h, and it's defined on the upper half plane. Okay, so we have this this object, and then what do you do? What you do is you try to show that the law that you get when you integrate over the randomness of the path actually is a Gaussian free field. Okay, so that was I just described the first step. And then the next thing that you do in this program is you try to show that the marginal law of h, so in other words, after you integrate over the randomness of the path, so after integrating over eta, this is a Gaussian free field on the upper half plane. Okay, so we've just described a distribution in kind of a complicated way. We know that when you condition on the path, it's given by a Gaussian free field on the complement of the path, but it's not a priori clear that this actually defines a Gaussian free field. But if this construction is supposed to be describing a Gaussian free field flow line, then it better be that, once you forget about where this path is, we're left with a Gaussian free field. Okay, and then upon doing this, the last thing that one would want to show is that the path that you built, eta, this is determined by the Gaussian free field. Okay, and this is actually not clear from the construction. It's not immediate from the construction. Because in order to build H, we first picked eta. Okay, so these are kind of the three things that one would want to do to build these Gaussian free fields in this sort of indirect way. And again, the function of the Gaussian free field that should give you these paths should be what you get when you take the Gaussian free field and you somehow regularize it in this way, construct the flow lines in the usual way, and then send epsilon to 0. But no one knows yet how to make that program work. So that's a very interesting but seems to be hard open question. All right, so now what I want to do is just tell you a little bit of history about this construction before we go more to the math. So these these Gaussian free field SLE couplings, these go back first to a work these go back first to a work of Schramm and Sheffield. This was first posted to the archive in 2006. And what they do here is they show that if you take the discrete Gaussian free field and then you look at its level sets, so these are well defined because the discrete Gaussian free field is a function, and these discrete Gaussian free field level sets, these converge to SLE4. Okay, so they had this big paper in ACTA, first available I think in 2006, and then construction in the continuum was described by Scott. And this is what we're going to be doing today. The construction of these flow lines in the continuum using the procedure that I just went over. And then what we're not going to have time to do, but is a very interesting argument that goes back to Julian Dubeda, and that's that he carried out this last step. So he showed that the Gaussian free field almost surely determines its flow lines. So he has this very clever argument, which is based on, if you've heard of this, it's based on something called duality in SLE. And since then, this type of result has formed, this general idea has formed really the basis of a number of subsequent works. All right, so now, before stating the mathematical result, I want to make one other remark, and that's that here we're looking at e to the IH and the relationship between SLE and the Gaussian free field in this sense. And in the course that Remy is looking, that Remy is giving, he's looking at what kind of objects you can build with e to the gamma h, where gamma is real. Okay, so what are we doing for today's topic? Is sort of studying or making sense of the flow lines of e to the IH, where h is a Gaussian free field. It's natural to ask, though, what happens, or what relationships are there? Let me say it that way. What relationships are there between SLE and e to the gamma h? And it turns out that there's also a companion coupling, companion SLE Gaussian free field coupling, which has a natural interpretation in this sense. And we're not going to spend much time on this, but let me just explain what the basic idea is. So there's another coupling, also due to Scott. And it's the one which is, again, it has a natural interpretation when you think of it as somehow as corresponding to these Liouville quantum gravity measures. And what it is it's the continuum analog of the following procedure. So let's suppose that we have, let's say, two planar maps. Let me try to draw. Okay, so this is supposed to be some kind of a planar map, and maybe I have another one. I guess this is not a quadrangulation. But anyway, you have two maps like this. And if you have two of these maps that have boundary, then there's kind of a natural way to glue them together just by identifying their boundary segments. And if you do that, so you start off with your two maps, and you glue them together, then you're going to get a big map where this is the interface between the two of them. So let's say this is map 1, and this is map 2. And when you glue these guys together along part of their boundary, then you're going to get a big map and some kind of interface between them. There's a very natural gluing operation that you can perform. And the other coupling of SLE with the Gaussian free field, which again won't be the main focus today, is that you can do kind of the same thing in the continuum, but with Liouville quantum gravity surfaces. And what this coupling says is that when you sort of weld these together in this fashion, then the interfaces that you get between the two chunks of surface are going to be SLE-like curves. And these two couplings actually also play well with each other. And unfortunately, this is something that we don't have time to talk about. But these turn out to be very closely connected. So e to the IH and e to the gamma h. All right, so now what I'm going to do is I'm going to state the basic SLE Gaussian free field flow line coupling result. And the statement of this that I'm going to give is based on Scott's paper on this topic on the what he calls the quantum zipper. So here's the theorem statement. Due to Scott. And what I'm going to do for convenience is I'm just going to fix kappa between 0 and 4. And then I'm going to let chi be a kappa-dependent constant given by 2 over the square root of kappa minus the square root of kappa over 2. And because kappa is between 0 and 4, you'll notice that this is always positive. And then I'm also going to let lambda be the constant given by pi over the square root of kappa. Okay. And then I'm going to fix a Gaussian free field on the upper half plane. Okay. And I'm going to let calligraphic h sub 0, this is going to be the harmonic function. So it's the function on the upper half plane with boundary values minus lambda on R minus, so the negative reals, and lambda on the positive reals. Okay, so here's the picture you should have in mind. So this is the upper half plane. Here's the origin, and this harmonic function is just the one that has boundary values minus lambda here and lambda over here, where lambda is that kappa-dependent constant. All right. Then what I'm going to do is I'm going to let eta be an SLE kappa curve sampled independently of h. I'm going to let G sub t be its Loevner flow. And I'm going to let F sub t be given by G sub t minus Wt, where here W of t is its Loevner driving function. Okay, so I have my SLE curve. All right. And then what the theorem says is if you let what I'm going to call calligraphic h sub t be given by h0 composed with f sub t minus chi times the argument of ft prime, then it's true that your Gaussian free field plus this deterministic function is equal in distribution to h composed with f sub tau plus h sub tau for any eta stopping time tau. Okay, so that's the theorem statement. Now let me draw a picture up here to illustrate it. So So what we're doing on the bottom here is we are drawing our SLE curve, eta, and this is eta of tau here at the top. And then we're doing exactly what I described before. We're taking our Gaussian free field with certain boundary values, and then along the curve, we're giving boundary values for the Gaussian free field. This is the the calligraphic h sub tau that you see on the right-hand side. We're giving boundary values for our Gaussian free field here, which are given by what they would be if this were a flow line of an honest vector field e to the IH. And the theorem statement is that the field that you get down here, which is the one which is described on the right-hand side up there, has the same distribution as just the Gaussian free field in the upper half plane with boundary values minus lambda and lambda. Okay. All right, and so this is the theorem that I'm going to indicate the proof of now in the last 20 minutes or so. Before I do that, let me just make a couple of remarks. So the boundary conditions in the theorem statement these are the ones that are necessary so these are such that the flow line of the Gaussian free field is just a regular SLE kappa. Okay, so if you take minus lambda lambda boundary conditions, then the Gaussian free field flow line from the origin is SLE. If you change the boundary conditions, if you change the boundary conditions, then what do you get? This leads to SLE variance, the so-called SLE kappa rho processes for your flow line. Okay, and yeah, the proof of this theorem is essentially the same for the SLE kappa rho processes for general boundary values. So for simplicity, we're going to stick to this case here. All right, so now let me go through the idea of the proof of this theorem. Okay, so what do we know? So we know that here, h plus h0, this is a Gaussian field. Okay, and well, it's true that this is going to be a Gaussian field, with its given law, if and only if it's true for, say, for all C infinity test functions. So compactly supported C infinity test functions in the upper half plane, we have that h plus calligraphic h0 integrated against phi, this is a normal random variable. So this is normal with mean, let's say m0, which is just given by the integral of calligraphic h sub 0 against phi, and variance given by e sub 0, which is the integral of phi of x against the Green's function on the upper half plane. So this is the Green's function on the upper half plane. Okay, and this property completely characterizes the law of h plus h0. Okay? So just knowing that for any fixed test function, what you get when you integrate the field against that test function has this form determines the entire law of this field. Okay? So what this means is that in order to prove the theorem, what we need to do is we need to show that if we take h composed with f sub tau, and we add that to calligraphic h sub tau, and we take their L2 inner product, then this has the same law. Okay, so this very convenient property of the Gaussian distribution means that we only have to check one test function at a time. And this simplifies the problem quite a lot. Okay, so in order to check this, what do we have to do? All that we have to do is we have to show that, or we want to show that if we look at the characteristic function of the integral of h sub tau, or sorry, h composed with f sub tau plus h sub tau against any test function, then this has the right form. It's the characteristic function of a Gaussian random variable with variance E0 and mean given by M0. Okay, so this is what we have to do. We just have to do this, this calculation of this characteristic function. So that's our goal. And what do we know? Well, what we know is that if I let f sub t, so this is, oh sorry, if I let calligraphic f sub t, this is going to be the sigma algebra generated by my SLE path up to time t. So this is the same thing as the as the sigma algebra generated by the driving function up to time t. Then we know that that f sub t, the centered Loevner map at time t, is this is something which is ft measurable. Of course, because if you see the path, you can determine what the Loevner flow is. And the way that we're going to use this is that this then tells us what the law is of the first term in this characteristic function that we want to compute when we condition on f sub tau. Okay. So in particular, given f sub tau, we have that the Gaussian free field H composed with f sub tau. This is a Gaussian free field on the upper half plane minus the curve up to time tau. So here we also used the conformal invariance of the Gaussian free field. Okay, so in this tells us that if I integrate h composed with f tau against phi, then given f tau, this is a normal random variable with mean 0 and variance e tau, where here, for a given value of t, I'm going to let e sub t be given by the integral of phi of x against the Green's function in the domain minus the path. So here, this is the Green's function for the Laplacian in the upper half plane minus the path up to time t. Okay, so conformal invariance gives us that. And so this allows us to start computing the characteristic function that I wrote down just a moment ago. So let's do that. Let's plug this in. All right, so we just insert this into this expression over here. So let me copy it. So we can start to calculate this characteristic function. So this is e to the I theta h composed with f tau plus h tau integrated against phi. So to calculate this, I can take a conditional expectation given f tau, and I'm going to leave this first part in there. So I have e to the I theta h composed with f tau integrated against phi. And since this second variable here, this calligraphic h sub tau, this is determined by the Loevner flow at time tau, this is actually measurable with respect to this sigma algebra. So I can just pull it out, and I get this expression here. All right, but we know that given f tau, this is just a Gaussian free field integrated against this test function. So we can calculate this this conditional expectation here. It's just going to be given by minus theta squared over 2 times what I called e sub tau. Okay, so we took care of that part, and now I'm just going to copy in the second term here. Okay, and now we just have to work with this expression. All right, and to show that this is equal to that this expression here that this is equal what we want it to be equal to. So let me call this over here star. What do you have to do? Well, it suffices to show that this first term, this first guy here, which is given by integrating h sub t against phi in the L2 sense, what you want to do is you want to show that this is a martingale with a certain quadratic variation. So with quadratic variation given by minus d e sub t. Okay? Because if you show that, then this is just going to be an exponential martingale associated with this martingale, and so you're done. Okay, so that's the main thing you have to do in the proof. And this is actually not so bad to do because everything in these expressions here is explicit. There are formulas for everything, and so you can just compute to get that this is the case. So I'm not going to do the calculations, but let me just tell you that showing this, this is just an exercise in stochastic calculus. Practice using Ito's formula. And it's not so bad to do. And the reason is that everything is explicit. In particular, the Green's function, g of xy on the upper half plane, this is just given by minus the log of x minus y plus the log of x minus y bar. And then by the conformal invariance of the Green's function, this g sub t that appeared in my definition of E sub t is explicitly given by g of f of t of x, f of t of y. Okay, and so since this, this is pretty explicit here, and these f sub t's, these just satisfy, they satisfy stochastic differential equation that I wrote down during the beginning, and so you can just you can compute and you can verify that this is in fact the case, and that will complete the proof of the theorem for you. Okay, and if you want to see the details of this calculation, if you look at Scott's paper on the quantum zipper, he carries them out. I think he does almost all of them, actually. So you can find it there. And so in the last few minutes, let me just make a few remarks. So, so first of all, the proof of the coupling for other kappa values. So in particular, kappa equal to 4 or kappa bigger than 4 is the same. Essentially the same. The main difference here is how you interpret these objects in terms of the Gaussian free field. The difference is just in the interpretation. And the way it works is that when kappa is between 0 and 4, which is the case we focused on today, you get flow lines. When kappa is equal to 4, this is the original case due to Schramm and Sheffield. The interpretation is that these are Gaussian free field level lines. This gives you a way to make sense of what should be the level sets of the Gaussian free field. And when kappa is bigger than 4, that's the last case, we've adopted the terminology counterflow line now. We call this a counterflow line of the Gaussian free field. And let me just explain really quickly the reason for this terminology. So the important thing is that if you go back to this constant chi that I wrote down earlier, so chi is equal to 2 over square root kappa minus the square root of kappa over 2, then this has a symmetry, and that's that chi of kappa is equal to minus chi of 16 over kappa, where here kappa is, let's say, between 0 and 4. Well, it doesn't really matter. Kappa is just positive. Okay? So you have this relationship between chi of kappa and chi of 16 over kappa. And where this chi comes in is in the change of coordinates formula for the Gaussian free field. And what this tells you is that couplings between SLE kappa and SLE 16 over kappa, these are somehow, they somehow play well together in the Gaussian free field. So they fit together in the SLE Gaussian free field coupling. And, okay, so the reason for the terminology counterflow line is that it turns out that an SLE 16 over kappa curve, where now kappa is between 0 and 4, this can be constructed as sort of a tree of SLE kappa flow lines which go in the opposite direction. And I hope to show you some pictures of this in the last lecture. So somehow you can put SLE kappa and SLE 16 over kappa curves together using the Gaussian free field. And in this coupling, the SLE kappa curves are somehow naturally traveling in one direction, let's say up, and the SLE 16 over kappa curve somehow naturally travels in the opposite direction. And somehow you can build an entire SLE 16 over kappa curve as some kind of tree which consists of these SLE kappa flow lines. Okay, and now let me just tell you in the last minute what we're going to do. What we're going to do next. So what we just did now, this kind of describes how you couple a single SLE curve with the Gaussian free field. And what we're going to look at next time is a theory of what are called local sets of the Gaussian free field. And basically, what a local set is, this is a random set, or possibly random set, coupled with the Gaussian free field that satisfies the Markov property. And important examples of local sets that we'll see are, first of all, deterministic sets are local. That's just the Markov property. I'll explain this more next time. But the other example, important example of a local set for us are going to be SLEs coupled as flow lines or counterflow lines. And the important property that these local sets have is that if you take unions of local sets, then you get another local set. And so once you know how to put one SLE with the Gaussian free field, then you can put many SLEs with the Gaussian free field by using the fact that these are local sets, and local sets have this kind of magical property that you can take their union. And that's what we're going to do next time. Does anybody have any questions? Yep.
I mean, so for this HT you defined, is there any intuitive explanation of why? I mean, what does this form?
Sorry. So you have
on the
right.
Top right.
Right.
You define HT in this particular way. Is there a more intuitive explanation of this?
Oh, so what it actually is? Yeah, so H sub t, So let me explain that. So let me erase this here. So h sub t is actually what's giving you the boundary values of the Gaussian free field along the path. And remember, h sub t is equal to this function h sub 0. Let me ignore that for a moment. Minus chi times the argument of ft prime. And so if this is your path here, so let's say this is eta up to time t. And then this is your centered Loebner map, which takes you back. Okay. Then ft inverse, the inverse of this map, if you run it along the boundary of the upper half plane, then this is giving you a parameterization of your curve. So if you kind of travel in this direction, let's say, then you're going to be traveling up your, sort of along the curve. And the argument of the derivative, this is just saying that what this corresponds to are the directions, the sort of tangential directions along the path. Now, of course, an SLE curve is a fractal curve. It's not a smooth curve, so it doesn't actually have tangent vectors. But the way that you should think of this is that this is the harmonic extension of what would be the tangent vectors if it had them. And this is supposed to be, what this is supposed to be saying is what I said earlier, and that's that the boundary data of the Gaussian free field along the curve is what it would be if this were a smooth function. So it just says that the vectors along the curve point in the way that they're supposed to. Now, what I said was also a little bit of a lie, because there's also this term here. And basically what this term corresponds to is if you were to draw in the vectors of the Gaussian free field of this vector field, should they exist along the path, then they would not point in exactly the same direction as the curve. So it turns out that what happens is that if you're on the left side of the curve, the vectors tend to point a little bit inward. And if you're on the right side of the curve, then the vectors also point a little bit inward towards the path. Okay, so kind of near the path, vectors don't point in exactly the same direction as the path, but they point a little bit inward sort of towards it. And for those people who know about this, this is sort of the kappa not equal to 4 analog of what Schramm and Sheffield called the height gap for the level lines of the Gaussian free field. So it turns out that for Gaussian free field level lines, they don't look like sort of honest level lines. They look like a cliff. Like sort of on one side the field is higher and the other side the field is lower. And the kind of analog of that here is that the vectors of this vector field, if they existed, kind of point towards the curve. It's sort of a stable direction. And and so this is sort of encoding all of that. Does anybody have any other final questions? All right, so I guess I'll stop there.